Hey guys, it's Simon and welcome back to my LibGDX Kotlin tutorial. The last time we learned how to render a sprite to the screen, and we also learned a little bit about the viewports, and currently we have this window here. So it's already in the correct aspect ratio of our game. We have our player ship here, but nothing else can be done. So no movement at the moment, no game mechanics, whatever. And from now on, we are improving on that. And we are introducing the so-called entity component system pattern that in the Java tutorial that I made a couple of months or years ago, I introduced it at a very late point in the project, and there was the feedback from a few users that I should have introduced it from the beginning. And in my opinion, they are correct, because the reason is when you use the entity component pattern, the way you structure your code and you set up things is completely different to the usual inheritance normal behavior, I would say. And that's why we're going to introduce it from the beginning, and this is what we are going to capture in this part. So it now takes a couple of parts until we add our different game mechanics step by step, and we start with this one here now. One thing before we go into that is that I wanted to mention that I forgot something in the last part, and I talked about the disposing of things, so like the texture and so on, and there are a couple of other things that needs to be disposed. There is a so-called disposable interface in LibGDX, as you can see here, and a couple of classes extend from this disposable class, and if it extends this one, then you really need to actively call the dispose method, and we forgot to do that for the patch, and I added that now. So in our game class where we create the patch, then we also need to dispose the patch. And in addition, I added a debug line, which is always useful, which prints out what was the maximum amount of sprites in the patch. So currently we see here it's 1, because we only render 1 sprite. But if you would have like a tiled map in the background and a lot of game objects and so on, then it's always a good idea to keep track of this number, because if it's too low, you could call the sprite batch with a different parameter, so with a better size. I think the default one is 1000. Yes, correct, 1000. You could reduce this then to, I don't know, 50, 100, whatever is your need to improve the memory usage of your game. Or if you have a lot more than 1000 sprites, then you should increase this number to reduce the total amount of render calls, that enough sprites are batched together in your game. This is the reason for this debug line. Okay, yeah, let's introduce the entity component system pattern. I think it's also described in the game patterns link that I linked in the video description of this tutorial. But we want to explain it a little bit more graphically, let's say, and I prepared there something in Paint. So don't take this as the perfect class diagram for this game. I just quickly came up with something how it could look like. And let's imagine in our game we have the player, we have the power-ups, and we have some timed events and so on. So maybe we would have a generic game object with the normal inheritance usage, so without the entity component pattern. We would have the game object. Then most likely we need to extend that, because some of the game objects are moving, so we have then movable game objects. So the game object usually has then most likely a render method or an update method. It gets then overwritten in the movable game object, which calls the code from the game object but has its own code. Then we might have some game objects which can move and also need to be rendered. So we might have then a drawable game object to draw things, and then maybe the combination, the movable drawable game object. And in the end, you get then a big tree in the end, depending on how big your game becomes. And at the bottom, you have then somewhere your player or your power up, and they are then extending from all the different base classes that you have. And debugging then usually becomes a hell, because if there is then a problem in one of the update methods, you need to go through this entire tree and check, okay, where in all these updates, overrides, and codes, where did I do the mistake? And when you change something in here, it has an impact on all the other things below at the end of the tree, which are somehow extending from that. And it gets a little bit messy then. In my opinion, it's still the nice or good approach for a very small game, and maybe in this game that we are developing now, it could still be used. Maybe that would be fine as well. But in my opinion, if you get then bigger and bigger with your game, then I, at least personally, would always recommend the entity component system. It's a little bit of a personal preference, but I like it because it really splits up the things in your game logically in certain modules, and the way you're gonna develop it is really nice because nothing is impacting each other, and you can really program on one specific module and finish that, and it has no impact on all the other things, which is nice. We're going to learn that in the upcoming parts. So this would be the usual inheritance. But we are going to use, as mentioned, the entity component pattern. And what is that? It looks a little bit like this. So you have a generic entity, which is normally nothing else than a unique ID of your game object, let's say. So the entity itself, it only has an ID and nothing else. So it's stupid, it cannot do anything. And yeah, it's just an object there. And to give it then certain properties, let's say you want that your entity can move. Then you define a move component with some properties like the speed, I don't know, the acceleration, the maximum speed, whatever you need for a movement in your system. Then you can say, okay, this entity that I create can move, so add the move component to it. Or in my example here, I want a player component, so I know it has some transformation on the screen, so it has a certain position, a certain size, a certain rotation. So that's why I want my player entity to have the transform component. Then I want that it can be rendered, that there is graphic on the screen. So I also add the graphic component to it, which contains the graphical part. And I want that it's recognized as a player component because with the player we want to do certain things like tracking the high score, interacting with the input of the mouse or the finger to move the player and so on. So that's why we also add the player component to it, that it's recognized as a player. And as you see here, there's no tree actually happening, so there's no inheritance. You just have your entity with the ID, and then you add certain components to your entity that it gets certain properties. And how are these properties then used? These are used in so-called systems. So that's why it's called entity, component, and then system. And the system is then nothing else than it iterates usually over all the entities which have a certain type of components. So for example, our move system, there we want to do something with entities which have a transform component, so they have a position, and which have a move component. Then our move system knows what it should do. So it should then place the entity so that the position of the transform component should be updated with the move specifications of our entity. And this is then a modular system. It does not care how many entities we have or what kind of entities we have. As long as there are entities which have a transform and a move component, this system will be updated, and it updates then all entities with those two components. And these systems now we are going to develop in the upcoming parts, and there are several different ways to do that, and we're going to learn that. But keep in mind, again, so entity, it's just a unique ID of an object, components which can be added to an entity, and then systems which are updating the data of the components. So the components is nothing else than a data dump, let's say, of several attributes that you need to do certain mechanics or logics in your game. Okay, with LibGDX, there we have the Ashley entity component system, which is coming with LibGDX, and we already added that to our project. And Ashley has then, of course, certain things, how to create entities, components, and how to handle systems. And the first thing that we need is a so-called engine. So the engine is like the core of the entity component system for Ashley. It it stores all the different entities, it stores the different systems, and it's then updating that. It makes a call to the update method of the different systems, and the systems are then processing the different entities. We see that in a moment, actually in the next part then, how that looks like. In this part, we are going to make our player an entity, so the thing that we already have in place, and we convert that now to an entity with several components. And we use a so-called pooled engine. So let's call it an engine. It's an, I think engine is actually the base class, yes, of Ashley. And we do, again, a lazy initialization because we only want to initialize it the first time where it's used. And we use a so-called pooled engine. A pooled engine has several parameters again for the pool size, maximum pool size, for entities, and the same thing then for components. We use the default settings for the time being. I forgot to make it big, sorry. So we use the default size for the time being. So we have an initial entity size of 10. We have maximum of 100 entities, which should be fine for our game. I think we have at most maybe 10 entities on the screen at once, so we could actually reduce that. And we have a size for the component pool and a maximum size for the component pool. And what is now the difference between a pooled engine and an engine? So again, the engine is the core concept, so it stores the entities, component systems, whatever, and does the updating and everything for us. And the pooling is now something in addition, which is, in my opinion, important when you develop games with a VM language like Java or Kotlin. Because usually when you develop Java, you initiate objects like, I don't know, and you hash map a new object, you use it then somewhere, and at one point it gets then maybe removed from a cache or something, and the garbage collector then takes care of removing all these objects which do not have any references anymore, and it cleans that up. But when the garbage collector is doing something, this is actually taking some processing time, and in your game you would the player would then experience some lag or a spike, because when the garbage collector is cleaning up things, your game logic or your game cannot be processed, and there is the picture or the image is then stuck, which is not a nice experience for the player. That's why there's the concept of pooling, which is introduced in LibGDX and which is Ashley also using. And the idea behind that is that you have, let's take again our entity as an example. So we have an entity, and when we initialize it, it has nothing. So no components, it just has its ID, and that's it. And instead of then removing the reference to the entity if we no longer need it, we actually put it back into a pool. So we know now in this pool there are objects which are no longer used, and if we need a new entity, then we are actually retrieving it out of that pool again. So throughout the game, our pools will increase in size, because whenever we want to free a certain object, it gets put back to the pool. And if we need a new object, we put it out of the pool. If the pool is empty, we create a new instance, of course. But if there's already a freed entity in the pool, then we use that one. And with this specific concept, we avoid triggering the garbage collector, because actually we are never freeing objects really. We are always putting them back into a pool and retrieve it then out of the pool. We see that in a moment with the components. And that's now the difference between a normal engine, where you always create new entities, new components, and they would be freed normally with the garbage collector, and the pooled engine. In the pooled engine, the components and the entities are pooled, as you can already see it here. So they are not really freed by the garbage collector. Instead, they are moved back into the specific pool and then reused later on if we need another entity or component of a specific type. This is the pooling concept, which you can use actually for certain other things as well. There's an article on the LibGDX Wikipedia page, which I will link in the comment of this video. Okay, so since we have now our engine, we want to update our engine. And for that, we have our game screen. And in our render method, where we are currently really rendering, before we do any kind of rendering, we are going to update our engine. And currently we don't have access to our engine, and most of our screens, I think all screens actually will use the engine. So that's why we also allow our screens to have access to it. And let's introduce a new one, which is an engine. And it's actually the game engine. Okay. Then let's go back to our game screen. So now we have access to that, and now we can write engine, and there is an update, and there we put in the delta time. I did not explain that yet, but I can do it now actually. So we know already that the render method is called per frame. And there is a specific time between two frames, and the time that has passed between the last frame and the current frame is passed into the render method as this delta. It's a float value. And with that time, usually you do some certain scaling and so on. So for example, let's say you want to move 10 units per frame. Then if you would just call it if you would here have something like, I don't know, entity x plus equals 10, that would be the first approach most likely that you would come up with, then this is not a good approach, because you can imagine the render method is called a different amount of times on different devices. So if it's 60 times per second, then our entity would move 60 times 10 fields on the x-axis. But if we have a slow device and we actually have 5 frames per second, then it would only move 5 times 10 per second. And then imagine a multiplayer game. Players with different devices are moving in a different speed. This is of course not the intended behavior that you want to have. That's why most of the time, and in more advanced game developer games, let's say, you see then a multiplication by the delta, because then you make sure that no matter what the frame rate is, you always move at that specific amount of range within a certain period of time. I hope that makes sense. If not, let me know in the comments, then I can explain that in more detail if you want. Good, but with that, so with the update method is actually a description. What it does, so it updates all the systems in this engine, and we create actually the first system then in the next part. But this is needed for the processing that I mentioned before, so that all the different entities with the different components get then updated accordingly through systems. Good, then the next thing there is of course a KTX extension for Ashley. So we open up our build Gradle file of the core project, and there we add a new extension. So I think it's called KTX Ashley if I'm not mistaken. Now let's refresh. Good, I think that should be it. And now we are going to create our first components. So for that, we go into our core project, then we create a new package actually. I always call it ECS for Entity Component System, and then another one for components, and another one for system. And in this part, we're focusing on the component, so we are going to add a transform component, and we are also going to add a graphic component. Okay, first let's go to our transform component. So what it needs to extend the component class from Ashley. And since we have a pooled engine, we should also extend from poolable. This is a GDX interface. What poolable is doing is that you need to specify a reset method. So this is what I mentioned before. When the object, in this case a transform component, would get freed and added to the pool of transform components, then the reset method is called to reset any kind of data which was added to or adjusted for this specific component. So let's say you move it back to the initial state, so that when it would get out of the pool again, so if you reuse it, then it has its initial values again. For our transform component, we use following things for the time being. So we have a certain position. As mentioned, this is always actually a vector 3 instead of a vector 2, because OpenGL is always we only have a 2D game, but OpenGL in the background is still a 3D graphic language, and that's why we always have this set component as well. And since we have to use it, we use here a position which is a vector free, but the set coordinate will always be 1 or 0 most likely, so we don't really use it. Then we have a size, which is just a vector 2, so there we only need 2 values, and the default size is maybe 1, 1, 1, so 1 world unit wide and high. And then we also have a rotation, if we want to do that in degrees, which is 0. And there's something that I personally do not like a lot, but I don't know how to improve on that. So in the reset method, I actually want to set now the same values as here. So you need to duplicate the code a little bit for the reset stuff. And I don't like that a lot, to be honest, but yeah, it is how it is. If you have a better idea how to improve on that, please let me know. So whenever we want to reset the transform component, we set our transform position actually to the 0 vector again, so that we are 0, 0, 0 for all of them. For the size, we set it back again to 1, 1, and the rotation is 0 if it gets reset. So don't forget that whenever you add something new here to a component, always think about what needs to be done in the reset case to reset it properly. Because if we would not do that, let's say we have a size of, let's say we forgot to reset the size and we scaled our object to maybe 5, 5. Now we create a new entity, and instead of having then the value of 1, 1, if the transform component is coming out of the pool, it would have the size of 5, 5 from the entity from before, which of course is not correct. So that's why always make sure that you reset everything correctly, otherwise you might get some strange behavior. Okay, and every component always should come with a so-called component mapper. So I just write it down what that means. So this is the first KTX extension that we use, so a mapper 4. We want to have it for our transform component. And what that does, it helps to make the access of the transform component of an entity faster. So usually I think it's a hashing lookup. So if you write something like entity get component transform component, then I think it's a hash lookup, and this has the complexity of O log n from what I remember. And with a mapper, you actually improve on that, because then instead of O log n, it becomes O1. So it's like accessing a certain index of an array. You see here provides O1 retrieval of components for an entity. And how does that work? So first of all, companion object, be careful with that, because it's I think it's like static in Java, and on Android that could be a problem if your static variable contains some state, because on Android phones it can, or on Android itself, it can happen that static stuff gets removed temporarily from the memory to free it up for other things. So let's imagine you run your game and now your mother calls you. Now the phone does not have enough memory for the phone call, so it removes first of all the static stuff, and the other stuff of your game, if it still fits in there, is there and it runs in the background. Now you can't, or you stopped talking to your mother, you go back to your game, and now it would reinitiate all the static stuff again. But as mentioned, it will not restore the state. So if your static variable contains any kind of state, it would be lost, because it got removed before and now reinitiated newly. With the component mapper, we don't have this problem, because it does not store any state. What it does, so it's the out of the box Ashley stuff component mapper get for a specific class. What this is doing is just returning a new component mapper. And there we end up then in this class. And there I did not look into the details, but the way I imagine it is that there is for every component type, it has an object map in the background, so it stores the type in this map, and the component mapper is then just retrieving the index of this object map. So object map is like an hash map. It's the LibGDX hash map, let's say. And it retrieves the index for that specific component type. And then the mapper knows that instead of hashing the value and looking it up, it knows it's at this specific index, and it can call it directly like an array accessing. So it's O1 instead of O log n. Good, and with that we have our transform component. So if we add now this to our entity, it has a position, a size, and a rotation. The next thing would be our graphic component. There we have the same thing. So graphic component extends again component, poolable, reset method, the basic stuff. And the only thing that we need for our graphic component currently is a sprite, and there we initiate it with nothing. So no texture, no nothing. Actually, if we would call now sprite draw, I think it would throw an error because we don't have a texture, but we come back to that later on. So for the time being, this is enough. And in our reset method, we want to clear the texture that we set then in the next part correctly with a system and so on. For the time being, we have it like that. So the texture would be cleared so that we don't reuse a wrong texture maybe from a previous entity if we forget to set it for the new one. And we also want to reset the color. So if the color got changed to something else, reset it again to white, which means that the normal colors of the texture will be used for the rendering. And again, never forget the component mapper. In the next part, it makes more sense what this mapper and so on does for us and how it can help us. Okay, so we have our transform component, we have our graphic component, and now we can rewrite the stuff in our game screen. So instead of having here texture and sprite sets that way, we will actually make now a player entity. So it's just for in this part. In the next part it will be solved in a different way, but for the time being, to understand now how this component is working together and how it works, we will make now our first entity. So we will make a player entity. There we use again a KTX extension, which is called entity. Or is it? It's not entity, it's game. It's an extension of the engine, which is called entity. So this is the KTX extension. Then we want to say, so this is now like a DSL, so a domain specific language for an Ashley entity to create it. And there we can now specify we want to have the entity with a transform component and we want to have it with a graphic component. So we would get back here an entity with a transform and graphic component. We want to set our transformation a little bit differently. We can do that like this. So now we have access to our transform component properties, and the position is 1, 1, 0, for example. So this represents then this set position. And the size is already 1, 1 per default, so nothing else needs to be done. Then for our sprite here in the graphic component, we also want to set the texture already. So sprite, I think it's set texture. Yep. And there we use this texture actually here. So let's move that a little bit up. And let's rename it to, for the time being, player texture, to make it really clear here. And here we assign the player texture. Then we can get rid of our dummy sprite from before. And now here in the batch, instead of using the sprite, we will actually use our player. We need our graphic component mapper. So graphic component dot mapper. So this is how you can access the graphic component of an entity with it's again a KTX extension. This could return null, because if the entity does not have a graphic component, then it's null. Null is not that often used, I would say, in Kotlin, but since Ashley is a Java library and also LibGDX in the background is a Java library, that's why sometimes you get still here null values, but that's not a problem. So there we have the Kotlin null save operator. Then we can access our sprites and we can call the draw method and pass in our patch. This is how we had it before. And with that, we should actually now get the same result as before, but instead of just having a stupid sprite, we already have now an entity with several components, so a transform and graphic component, which now take over the job for us to storing certain information that we can then use. Of course, in the next part, we introduced then a render system, so we don't call this here directly the way we did it. We want to have a generic system solution to render any kind of components, but that is covered then as mentioned in the next part. So I had to look up a couple of things because I was not sure again how to initialize the sprite correctly, but that's why I have my GitHub account, because then I don't need to check it out again and again. I have already the solution. So for the sprite before, we just had the texture equals player texture, but this does not correctly initialize the sprite. We came up with a better solution in the next part. For the time being, we need to call set region. So this is actually setting the texture as we did it before, but in addition, it also sets the region. And this is important because if we don't have a region, then it's 0, 0, 0, 0, and then nothing is rendered because a width and a height of 0 is not visible, of course. So instead of texture equal, we need to call the set region like this. Then we also set the size initially. There comes now our scaling into place because the texture that we have is of course in pixels and we need to convert that into our world units. So now we use this unit scale constant that we introduced the last time, and for this game we have that 16 pixels are actually one world unit. So you need to convert that as well, the size. And then I always call the origin center. So this is used for rotating stuff that I think the point where you rotate around is then the center of the texture. With that, the sprite is correctly initialized, and then I changed also the render method here a little bit. So you see now here a little bit of a different code. Also that one will be improved in the later part, and I mentioned different approaches because currently, as you see, we get a lot of indentations with that and a lot of scope blocks, and that can be improved a little bit as well. So instead of it, we have now the explicit batch here. Then with the Kotlin let, so question.let, we have then a null save access to our graphic component. So if it's not there, this block is skipped. If it's there, we are inside this block and the graphic component is represented as graphic. Same for the transform component. And then we want to render the sprite. So here we know now it's not null because the graphic is not null, and therefore the sprite, the way we set it up, is not null. And then we set the rotation. We set the boundaries, so the position and the size of the sprite. And then we draw it. And when we run this now, let's do that. We should get the same result as before. Correct. So now we have still our player here at the bottom left corner. So with the position 1, 1, a size of 1. And instead of having now only the sprite, we're actually using already an entity. Good. And that's it for this part. So we created now our first entity and several components. And in the next part, we are going to develop then a render system that can be then used for any kind of entity. And we get rid then of this player specific block. And the engine then takes over for our rendering logic. Thanks for watching. Have a nice day and bye bye.